Today we're going to discuss additional examples of maximum likelihood estimation. What I have outlined above here should be familiar to you. So above is the method of maximum likelihood, and we're going to consider this example where our data comes from a Poisson distribution. So our first step is to collect data. We have our first step. So step 1 is done. Step 2 is to form the likelihood function. So you should notice, because these are coming from a Poisson distribution, they have the density function of a Poisson distribution, which is e to the minus lambda times lambda to the x divided by x factorial. And that is an x sub I because each of our observations has this density. So that is the density function of each observation. We now need to form our likelihood function. Our likelihood function is going to be the product of each of these density functions, where instead of I have x1 through x sub n, and this will look like e to the minus lambda times lambda to the x sub 1 divided by x1 factorial, and these multiply like this. Okay, now let's combine terms, and this will be x1 factorial times x sub n factorial multiplied through to the minus 1 power. The exponents combine, so e to the minus lambda, but there's n of them, so that will be n times lambda. And let's write n in a capital. Then there's lambda to the x here, where the exponents add, so that will be x1 through x sub n. Now, our unknown parameter is of the distribution. The only thing that's unknown here is the parameter lambda, so our goal is to estimate lambda. I'm going to take the log of the likelihood. So let's maximize the log of the likelihood. Okay, and if I do this, this will be minus ln of x1 factorial product with x sub n factorial. Now the multiplication becomes addition, so that'll be plus a minus n lambda, which is the exponent. Then finally I'll have plus and by the way, I had a teeny mistake here, which is that these are pluses. We're adding the exponents. I think I said that, but I wrote just dot dot dot. So this will be plus x1 through x sub n. And by the way, that's just a property of exponents. When you multiply them, the exponents add, times ln of lambda. Okay, so now our goal is to take the derivative and maximize this with respect to the unknown parameter with respect to lambda. So we take the derivative. This first term is 0. There's no lambdas in it. The second term is minus n because there's just a single lambda. Then I'm going to have plus x1 through xn. I'm going to write that as the sum from I equals 1 to n of x sub I times the derivative of ln of lambda. From calculus 2, that derivative is just 1 over lambda. We set this equal to 0, and our goal is to solve for lambda. Okay, well, solving for lambda, we clear the denominator, and we're going to get minus n lambda plus summation of xi from I equals 1 to n equals 0. And then we just solve. We get summation from I equals 1 to n of x sub I divided by n. And that's nothing more than the average. Okay, so that is the MLE of a Poisson distribution. And that was an example of working through. So if I had to label the steps, that would be the third step. And then the box is the MLE estimator. That would be an example of working through these steps and solving for the unknown parameter. Thank you very much.